So in chapter analysis of stress, let us understand today principal planes and stresses. First, let us consider a three-dimensional object which is acted upon by three-dimensional stresses in x direction px, y direction py, and in z direction pz. Then at any point of this stressed object, say O, there exist three mutually perpendicular planes on which the stress is wholly normal and shear stress does not exist on any of these planes. This maximum stress depends upon its orientation, as we have seen in the case of plane stress system. So the plane which carries the largest normal stress are called principal planes, and the largest of the three stresses, sigma 1, sigma 2 and sigma 3, which are acting along x dash, y dash, z dash direction, is called major principal stress, and the minimum of these three stresses is called the minor principal stress. The plane carrying the principal stress which is largest is called major principal plane, and the plane carrying minimum of these three stresses is called minor principal plane. So in this chapter we will just see two-dimensional loading, and let us take the example where the object is loaded biaxially. So there is P1 stress along x direction and P2 stress along y direction. In this object, at each point, there exist two planes on which there are only normal stresses and shear stress does not exist. So let us take that plane is A dash, C dash. Sigma 1 and sigma 2 are the two stresses which are normal and there is no shear stress acting. So these two stresses are the major and minor principal stress. The largest one will be the major principal stress, the smallest will be the minor principal stress, and this plane is called the principal plane. So in this chapter we will use transformation equations to derive the principal stress under two-dimensional stress. In analysis of stress, let us understand today transformation equations and importance of the transformation equations. Let us recall the plane stress system and normal stress Pn and tangential stress Pt acting on a plane inclined at theta. So this is a state of pure shear. All the stresses are of equal magnitude Q, and then two normal stresses P1, P2 acting in mutually perpendicular direction. So this is the plane stress system. We have discussed normal stress and tangential stress at an inclined plane. The normal to the plane makes angle theta with the x-axis, and Pn found was P1 cos square theta plus P2 sin square theta plus Q sin 2 theta, and Pt was found to be minus P1 minus P2 by 2 sine 2 theta plus Q cos 2 theta. Now using two trigonometric identities, cos square theta is equal to 1 by 2 1 plus cos 2 theta, and sine square theta is equal to 1 by 2 1 minus cos 2 theta. We can transform Pn as P1 1 by 2 1 plus cos 2 theta plus P2 1 by 2 1 minus cos 2 theta plus Q sine 2 theta. This gives us 1 by 2 P1 plus P2 plus 1 by 2 cos 2 theta P1 minus P2 plus Q sine 2 theta. Rearranging, we can write Pn is equal to 1 by 2 P1 plus P2 plus 1 by 2 P1 minus P2 cos 2 theta plus Q sine 2 theta. Take Pt as above, minus 1 by 2 P1 minus P2 sine 2 theta plus Q cos 2 theta. These two equations are called transformation equations, since they transform the stress component from one axis to other axis. Let us understand this transformation more clearly. Let us take the element P1 and P2 are acting along x and y axis, say x axis, whereas Pn is acting at an angle theta from the x axis. So let us say this is x1 axis. So this formula Pn is equal to 1 by 2 P1 plus P2 plus 1 by 2 P1 minus P2 cos 2 theta plus Q sine 2 theta transforms the normal stress from x-axis to x1 axis. We can take any value of theta and transform the stress along the corresponding axis. Suppose we take another axis x2, which is in perpendicular direction to the x1. Since x1 is at an angle theta with x, the axis x2 will make angle 90 plus theta with x-axis. Since the axis x2 makes angle 90 plus theta from the x-axis, to find out the normal stress along the x2 axis, we will put, instead of theta, value 90 plus theta in the same formula for the Pn. So let us put theta is equal to 90 plus theta. We get 1 by 2 P1 plus P2 plus 1 by 2 P1 minus P2 cos of 290 plus theta plus Q sine of 290 plus theta. Simplifying, we get 1 by 2 P1 plus P2 plus 1 by 2 P1 minus P2 cos 180 plus 2 theta would be minus cos 2 theta, and sin 180 plus 2 theta would be minus sin 2 theta. So we get here minus sin minus q sin 2 theta, or Pn along x2 direction will be equal to 1 by 2 P1 plus P2 minus 1 by 2 P1 minus P2 cos 2 theta minus q sin 2 theta. If we write P theta along the x1 axis, we have Px dash is equal to the same quantity 1 by 2 P1 plus P2. Since it is inclined at theta, we can use this expression plus 1 by 2 P1 minus P2 cos 2 theta plus q sin 2 theta. These two terms get cancelled, and what we have is Px dash plus Px2 dash is equal to P1 plus P2. So this is another good conclusion. It tells us the sum of normal stresses along two perpendicular axes remains constant to whatever angle the element is rotated, and also the intrinsic state of the stress element remains same, that it is subjected to the same stresses. So we can conclude that normal stresses acting on perpendicular faces of a plane stress element remains constant at all angles of theta. So from the transformation equations and this conclusion that the stresses along two perpendicular planes remains constant in total, we will go to principal stresses. In engineering problems, we are more interested in maximum stress, maximum normal stress, and maximum shear stress, mainly in design problems. So principal stress helps there. So next concept would be principal stress. In plane stress system, we have seen that the value of normal stress Pn and the tangential stress Pt varies with angle theta, as it is a function of theta. But in engineering problems, we are more interested in largest normal stress, which would act on the stressed element. The plane at which the largest normal stress acts is called principal plane, and the largest stress is called principal stress. In a three-dimensional system, it is found that at any point of the stress element, there exist three planes on which only normal stresses acts and there is no shear stress. The maximum normal stress is called major principal stress, and the plane at which the maximum normal stress acts is called major principal plane, and the plane on which the minimum normal stress acts is called the minor principal stress, and the plane at which the minimum normal stress acts is called minor principal plane. But we will take two-dimensional stress system in which the third stress is 0 and the maximum normal stress, which is the major principal stress, is denoted by sigma 1, and the smallest normal stress, which is the minor principal stress, is denoted by sigma 2. In order to obtain the values of sigma 1 and sigma 2, we have to maximize this expression, and which can be done by differentiating Pn with respect to theta and putting the value dPn by d theta is equal to 0, which will give us the value of theta for which the stress would be maximum and minimum. So by differentiating, we get dPn by d theta is equal to 1 by 2 P1 minus P2 minus sine 2 theta into 2 plus q cos 2 theta into 2. Putting 0 to this expression, we get 2 cancels, P1 minus P2 minus sine 2 theta plus 2q cos 2 theta, which is equal to 0. So we get P1 minus P2 sine 2 theta is equal to 2q cos 2 theta, or tan 2 theta is equal to 2q by P1 minus P2, for which we can write equal to q by P1 minus P2 by 2. So this expression gives us the value of theta for which the value of normal stress will be maximum or minimum, or the two values given by this theta will give us the value of sigma 1 and sigma 2, which are the major and minor principal stresses. Since tan 2 theta is q by P1 minus P2 by 2, drawing a right angle triangle, so that we have to find sine 2 theta and cos 2 theta. This side is q, this side is P1 minus P2 by 2, and the diagonal would be root of q square plus P1 minus P2 by 2 whole square, and sine 2 theta will be equal to q by r, and cos 2 theta will be equal to P1 minus P2 by 2r. Putting the values of sine 2 theta and cos 2 theta in the equation for normal stress Pn, we will get the major principal stress sigma 1. So we can write P1 is equal to 1 by 2 P1 plus P2 plus 1 by 2 P1 minus P2 P1 minus P2 by 2r, putting the value of cos 2 theta and putting the value of sine 2 theta, we have q into q by r. Simplifying this, we get sigma 1 is equal to 1 by 2 P1 plus P2 P1 minus P2 whole square plus q square into 1 by 4. So 1 by 4 P1 minus P2 whole square plus Q square is nothing but R square. So R square by R is cancelled. So we get 1 by 2 P1 plus P2 plus R is equal to sigma 1. So we can write sigma 1 is equal to P1 plus P2 by 2 plus R, or sigma 1 is equal to P1 plus P2 by 2 plus root of P1 minus P2 by 2 whole square plus Q square. So we have obtained major principal stress sigma 1 is equal to P1 plus P2 by 2 plus R. Now we have to find out minor principal stress, that is sigma 1 plus sigma 2. Sigma 1 and sigma 2 are acting on perpendicular axes. So we have seen the sum of normal stress acting on two perpendicular axes remains constant in plane stress system. Using that theorem, we can write P1 plus P2 is equal to sigma 1 plus sigma 2, where sigma 1 and sigma 2 are the major and minor principal stresses, and P1 and P2 are the two stresses acting on the stressed element in perpendicular directions. So substituting the value of sigma 1, we get P1 plus P2 is equal to P1 plus P2 by 2 plus R plus sigma 2. So sigma 2 is equal to P1 plus P2 minus P1 plus P2 by 2 minus R. This gives sigma 2 is equal to P1 plus P2 by 2 minus R. So we can write sigma 1 sigma 2 is equal to P1 plus P2 by 2 plus minus R. Putting the value of R, we also get sigma 1 and sigma 2 is equal to P1 plus P2 by 2 plus minus root of P1 minus P2 by 2 whole square plus Q square. So far we have found tan 2 theta is equal to Q by P1 minus P2 by 2. Sigma 1 and sigma 2 are equal to P1 plus P2 by 2 plus minus root of P1 minus P2 by 2 whole square plus Q square. When describing principal stresses and principal planes, we said on principal planes there are no shear stress, only normal stress are present. So let us prove that shear stress is 0 for this theta. So let us find out the value of Pt for theta such as tan 2 theta is q by P1 minus P2 by 2. So Pt is equal to 1 by 2 P1 minus P2 sine 2 theta. We can put value q by r for sine 2 theta plus q, and for cos 2 theta we can put value P1 minus P2 by 2 r. The first term in Pt is since negative, both the terms are equal and cancel each other. Just simplifying, we get minus P1 minus P2 q by 2r plus q P1 minus P2 by 2r. They simply cancel out and we get 0. So it is proved that the shear stress on principal plane is 0 when theta is such that tan 2 theta is equal to q by p1 minus p2 by 2. To conclude with, we have found the major and minor principal stresses, that is the maximum and minimum normal stresses acting on the two-dimensional plane stress system, sigma 1 and sigma 2 equal to p1 plus p2 by 2 plus minus root p1 minus p2 by 2 whole square plus, and orientation of the major principal axis or the direction of sigma 1, or we can say the direction of maximum normal stress, is such that tan 2 theta is equal to q by p1 minus p2 by 2, and along the principal axis or the plane in which sigma max is acting, the shear stress Pt is non-existent and is 0. Now let us find out the maximum shear stress. To obtain the maximum value of shear stress Pt, we shall differentiate Pt with respect to theta and put the value to 0. So that will give us the value of theta for which the Pt will be max. So differentiating, we get minus 1 by 2 p1 minus p2 cos 2 theta into 2 plus q minus sin 2 theta into 2. Putting this equal to 0, we get minus p1 minus p2 cos 2 theta plus, again this is also minus 2q sin 2 theta, or 2q sin 2 theta is equal to minus p1 minus p2 cos 2 theta, or tan 2 theta is equal to minus p1 minus p2 by 2q. This gives two values of theta. One is between 0 to 90 degree and other is between 90 to 180 degree. So maximum and minimum shear stress are at 90 degree. So if maximum shear stress is at an angle theta, the minimum shear stress would be at 90 plus theta. So if we put the value of theta in the tangential stress equal to 90 plus theta, it would give the minimum shear stress. So putting that, Pt min will be equal to minus 1 by 2 p1 minus p2 sine 180 plus 2 theta plus q cos 180, and write Pt min is equal to minus 1 by 2 p1 minus p2 sine 180 plus 2 theta is minus sine 2 theta. Similarly, cos 180 plus 2 theta is minus cos 2 theta. So we can write q into minus cos 2 theta. So we get Pt min is equal to minus minus plus 1 by 2 p1 minus p2 sine 2 theta minus q cos 2 theta. If we examine, Pt max is minus 1 by 2 p1 minus p2 sine 2 theta plus q cos 2 theta. Then Pt min is plus 1 by 2 p1 minus p2 sine 2 theta minus q cos 2 theta. So it is just opposite in sign and magnitude remains same. So we can write is equal to minus Pt max. So we can conclude Pt max and Pt min are equal in magnitude but opposite in direction. 80 plus 2 theta. This gives us sine 180 plus 2 theta will be minus sine theta. So only sign changes, 1 by 2 p1 minus p2 sine 2 theta, and cos 180 plus 2 theta would be minus cos 2 theta. So this becomes minus q cos 2 theta. So if Pt max is 1 by 2 p1 minus p2 sine 2 theta plus q cos 2 theta, Pt min is just negative of the maximum shear stress because only sign is changing and magnitudes are same. So we can write Pt max is equal to minus Pt min. So far we have found for maximum shear stress tan 2 theta is equal to minus p1 minus p2 by 2q and Pt max is equal to minus Pt min, and general expression for Pt is equal to minus p1 minus p2 by 2 sine 2 theta plus q cos 2 theta. So let us obtain the Pt max by putting value of 2 theta as found in this expression. So again, making a right angle triangle, we have this side p1 minus p2 by 2 and this side q, and this is the diagonal r. So r will be equal to minus root of minus p1 minus p2 by 2 whole square. So minus sign is unimportant here, plus q square. So sine 2 theta becomes p1 minus p2 by 2 minus sine by r, and cos 2 theta is equal to q by. So in order to get the maximum value of Pt, we will put the value of sine 2 theta and cos 2 theta obtained here in this equation. So we get Pt max is equal to minus p1 minus p2 by 2. In place of sine 2 theta we write minus p1 minus p2 by 2 r plus q cos 2 theta, and in place of cos 2 theta we write q by r. Simplifying, we have p1 minus p2 by 2 whole square 1 by r plus q square by r, which is nothing but p1 minus p2 by 2 whole square plus q square whole upon r. if we see the numerator is nothing but r square from this, so we can write this equal to r square by r, or finally r. So pt max is equal to nothing but r, and opening value for r we get p1 minus p2 by 2 whole square plus q square. So we get the value of pt max equal to root p1 minus p2 by 2 whole square plus q square. P1 and p2 are the normal stresses and q is the shear stress acting on the stressed element. So for a plane stress system, so far we have derived that if sigma 1 and sigma 2 are maximum and minimum normal stresses, that is major principal stress and minor principal stress, then sigma 1 sigma 2 would be p1 plus p2 by 2 plus minus root of p1 minus p2 by 2 whole square plus q square, or let us write it p1 plus p2 by 2 plus minus r. And orientation of the sigma 1 is such that if it makes angle theta with the x-axis, then tan of 2 theta will be equal to q by p1 minus p2 by 2. Similarly, we have derived if pt max and pt min are the minimum and maximum shear stress, then they are such that pt max pt min will be equal to plus minus root of p1 minus p2 by 2 whole square plus q square, or we can simply write it plus minus r. So the magnitude of maximum and minimum shear stress is equal to r. That means they both are equal, but their direction or the orientation is just opposite. Let us find another important relation. Let us subtract sigma 2 from sigma 1. So sigma 1 minus sigma 2 will be equal to p1 plus p2 by 2 plus r. This is sigma 1, that is sigma max, minus p1 plus p2 by 2 minus r. This is sigma min. So the first term gets cancelled. Sigma 1 minus sigma 2 is equal to 2r. Or we can say sigma 1 minus sigma 2 by 2 is equal to r. And we also see that pt max is also equal to r. So we can write sigma 1 minus sigma 2 by 2 is equal to r is equal to pt max. So now we have another important relation. pt max is equal to sigma 1 minus sigma 2 by 2. So if we know the major principal stress and the minor principal stress, we can easily calculate the maximum shear stress. So we can add another important relation here. pt max is equal to sigma 1 minus sigma 2 by 2. Now let us see what is the orientation of maximum shear stress. If the maximum shear stress makes angle theta p with the x-axis, then theta p is such that tan 2 theta p is equal to P1 minus P2 by 2Q, and with a minus sign. So if we look at this P1 minus P2 by 2Q, it is just inverse of Q by P1 minus P2 by 2. So we can write this equal to minus cot of 2 theta, where theta is the orientation of major principal stress or the maximum normal stress sigma 1. And we have trigonometric relation minus cot theta is equal to tan of theta plus minus 90. So instead of minus cot 2 theta, we can write equal to tan 2 theta plus minus 90. This gives us relation between theta p and theta, that is relation between orientation of the maximum shear stress and the orientation of maximum normal stress. It is such that 2 theta p is equal to 2 theta plus minus 90. This implies theta p is such that it is equal to theta plus minus 45 degrees. So we can conclude that orientation of maximum shear stress is at 45 degrees from the principal stress plane. So to conclude with principal stresses and so far the relations we have derived, besides these relations, sigma max sigma min is equal to P1 plus P2 by 2 plus minus root of P1 minus P2 by 2 whole square plus Q square, and maximum shear stress and minimum shear stress PT max PT min is equal to plus minus root of P1 minus P2 by 2 whole square plus Q square. We have orientation of the principal stress theta is such that tan 2 theta is equal to Q by P1 minus P2 by 2 by 2, and the orientation of maximum shear stress PT max is such that tan 2 theta p is equal to P1 minus P2 by 2Q, negative of this. And we have another important relation, maximum shear stress PT max is equal to sigma 1 minus sigma 2 by 2, where sigma 1 is the maximum normal stress and sigma 2 is the minimum normal stress. So these are the important relations which we have derived under the analysis of stress and the principal stresses.